Hey guys, so this is the last lecture I'm going to record for Chem 112, and then Dr. Paxton's going to take the last couple. So we're going to talk about another part of the periodic table trends today. We're going to talk about the main group. So, for that, let's go over to my slides. And let's start by talking about the periodic table main group. So the elements that are main group are basically these ones minus the lanthanides, actinides, and the transition metals. And then these are just kind of there because they are left over, so don't mind those. And so the trends in these families are divided by the metalloids. And so what you're going to see is some families will be consistent. So if you remember, the alkaline metals was pretty consistent, alkaline earth metals was pretty consistent, halides was pretty consistent, but that's because they're not divided by this metalloid line. So the elements on top of the metalloid line, the metalloids themselves and the one on bottom, are going to have distinct differences in reactivity because that's, you know, what metals and nonmetals and metalloids all kind of behave like is kind of characteristic reactivity. So, and then if you remember about beryllium is a kind of weird outlier to the alkaline earths family. So let's talk about this first group, this boron, aluminum, gallium, indium, thallium family. So if we focus on boron first, boron is mostly nonmetallic, and so the bonding that is most apparent and most common for boron is all covalent. And so many of you don't know this, but borax is commonly used as a detergent. Borates can be used as a flame retardant that we use for treating fabrics or firefighter materials. And then borosilicate is this example, so it's otherwise known as Pyrex. And silicate glass, silicon glass will shatter completely, but Pyrex tends to be non-shattering, and so it kind of cracks, but also it doesn't completely go into a million pieces. So the other thing I'm going to talk about with boron halides is that these are prototypical Lewis acids. So prototypical meaning that they're going to be a very good example for you to remember about what a Lewis acid is. And so if you think about BF3, BF3 has this boron in the middle and 3 fluorines. That doesn't fill its octet, and so it's able to accept another electron pair from a donor. Let's say the donor is ammonia. So if ammonia reacts with boron trifluoride, you end up with this ammonia-boron trifluoride Lewis acid-Lewis base complex, where this bond in between the two atoms is kind of a homo-lumo interaction between the homo of the Lewis base and the lumo of the Lewis acid. And so this is really nice. BF3 is often thought to be somewhat weak because the pi bonding from all of these fluorine orbitals stabilizes this molecule as well. So if you think about boron trifluoride, boron trichloride, boron tribromide, it's a little bit weird because the boron and fluorine are so small to each other that the boron trifluoride is the least reactive, even though fluorine is the most electronegative. So that's kind of like, you know, the weird outlier and the weird outlier get together and have kind of like a weird reactivity. So let's see if you guys can answer this question. Boric acid, H3BO3, or BOH3, these are two ways to write the same thing, acts as a weak acid in water. Whoops. However, it does not do so by loss of a hydrogen ion. So a weak acid is going to often lose a hydrogen ion, but it says that's not how this happens. Instead, it acts as a Lewis acid toward the hydroxide ion. Write a balanced equation for the reaction of boric acid with water. So if we do that, then what we can write out is that BOH3 plus hydroxide ion. So again, the Lewis acid is going to be an electron acceptor. And the Lewis base, so this is Lewis acid, and the Lewis base is going to be a electron donor. And so this makes sense because the boron doesn't have a full octet. This hydroxide has a negative charge, so it's a highly charged, highly dense molecule that can donate electrons. And so if we think about what's going on and we kind of draw out a Lewis structure, we can have something that looks like this, where these OH atoms are very similar to kind of the fluorines that are shown down here. And this OH now can form a new bond here, where this overall molecule has a negative charge. So now you've got this new interaction here, where this is your balanced equation for the reaction of boric acid with hydroxide, but we want to know what the boric acid reaction is with water. So let's go BOH3 plus H2O. So we know that the H2O is broken up into H plus and OH minus, right? There's a certain amount of that in water. And therefore you're going to end up with this molecule that I just drew, which is going to have an overall minus charge plus H plus. So for for full best practices case, we should probably say that's two H2Os and then a OH and an H3O plus. And so that ends up being your balanced equation here for the reaction of the Lewis acid and water to form this tetraborate structure and then hydronium ion. So that would be your balanced equation. Okay. So let's talk about aluminum, gallium, indium. Well, they get an honorable mention, but mostly we're going to talk about aluminum. So aluminum has a really high standard reduction potential. And so your aluminum can be reduced to the aluminum metal, so your aluminum cation to aluminum metal. Your zinc can be, this is just kind of a reference, so remember this one has a negative standard reduction potential. So this is very likely to be reduced. So the problem why that's not the case though is that the aluminum is covered with an aluminum oxide coating. So this is extremely non-reactive. And so even though aluminum is one of the most abundant metals in the earth, it's actually really difficult to get a hold of because of this alumina oxide overcoating. So this is an example of how electrolysis is used to kind of utilized to get the aluminum out. So you've got your graphite lining to your cathode, and then you've got an iron container, and then you actually have to melt the aluminum to be able to do this. And then what you do is you put in a carbon anode, and then the aluminum is reduced on this iron cathode, and the molten aluminum is basically siphoned out this way. And so you've got some oxygen gas, you've got some oxide crust, you've got some molten alumina, and then this eventually reduces to form your aluminum metal. So the other thing that's true is that your aqueous solutions are going to act as a Bronsted acid. So aluminum has a really high positive charge, and so it can pull electron density away from the water, which means that the water can be deprotonated to act as a Bronsted acid. Your aluminum is going to form ionic two covalent compounds with halides. So if it's forming with kind of the smaller halides, it's going to be somewhat ionic, and then it will have kind of a little bit more covalent character as it goes down. So aluminum chloride reacting with water will hydrolyze to form the aluminum trioxide and then release HCl gas. So then honorable mentions, gallium is typically just used as a dopant in semiconductors. It has interesting properties that are similar to neighbors such as silicon and arsenic, but it has different electron configuration, and so you can kind of change the electrons that you have for like proton, p-type, or negative n-type semiconductors by using gallium. And then indium and thallium both have this inert pair effect that we talked about before, where they kind of have lower oxidation states that are stable than they should have because of the inert pair effect of those S electrons due to the low placement on the periodic table. Okay, so let's talk about aluminum. What is the third most abundant element in the Earth's crust? It is very inaccessible. So it's a lot of us have it, but it isn't around. What's the main reason? A, it is difficult to access because it is deep in the earth. B, it is always combined with sulfur and phosphorus. C, it is covered with an inert oxide overcoating. D, it is combined in an iron aluminum spinel and must be separated. So I'm going to pause. You should pause. So let's talk about A. Is it difficult to access because it is deep in the earth? Well, we get a lot of things out of the earth, even though they're deep in there. So that's not going to be the right answer. So A is not true. B, it is always combined with sulfur and phosphorus. Well, that's not actually true at all because aluminum is a hard cation, and so it's actually going to be combined with oxygen. Sulfur and phosphorus are kind of softer nonmetals, and so those are going to combine with things that are soft, such as like mercury or palladium or something like that. It is covered with an inert oxide overcoating. So that is the answer, is that, you get aluminum when it's in the metal form, is malleable, is really nice, is lightweight, is used for a lot of different applications, but it's difficult to get because you have to do all of this electrolysis to convert it to that metal. So D, it's combined in an iron aluminum spinel and must be separated. So iron aluminum spinels are likely possible, but that's not, again, the main issue for aluminum access. So now we're going to talk about the carbon family. So carbon is going to be the nonmetal in that family, followed by silicon and germanium, which are nonmetals, and then followed by tin and lead. And so we can basically break it up into these three groups. In general, the group has an ability to form long chains of atoms with themselves, and this is known as catenation. So you can think about it in terms of like a carbon network. If you think about a rock salt structure from Chem 111, carbon in the diamond form takes that structure, but everything is carbon. In general, there's an oxidation state of +4 for all members, which is going to be a covalent type state. And then an oxidation state of -4 is possible for the carbon, silicon, and germanium. -4 for tin and lead is a little bit more difficult because they are in that inert pair effect. So they have the oxidation state of 2, which is going to be an ionic type of interaction in that oxidation state. So carbon and silicon are extremely different, even though they're in the same family. They have very different chemical reactivity, different properties, different bonding types that are common to them. Germanium, I couldn't find a lot of uses for germanium. And then tin and lead are pretty similar in terms of how they react and what they can be used for. So let's talk about carbon on its own. So carbon can form these multiple covalent networks with itself in its carbon form. And so this is an example of graphene sheets where everything is sp2 hybridized, and there's just sheets and sheets of sp2 carbon networks. So then if you think about taking these sheets and rolling them up on themselves, this is what's known as a carbon nanotube, which you can see here, and this is still an sp2 hybridized sheet. They also found that they can form these buckyballs. So Buckminster Fullerene was an architect at some point, I don't remember when, and he would make these huge architectural structures called geodesic domes. And so the scientist who found the buckyball named it after Buckminster Fullerene. And so there's these basically geodesic combinations of 6-membered, 5-membered, 7-membered rings that form into a sphere, which are basically sp2 hybridized as well. So carbon takes these kind of like fullerene forms. It can also form graphite, activated carbon, or coking, where you just have a bunch of carbon that isn't really in any uniform dimension. It's just kind of amorphous is the word that we use for that. And then also diamond, which has a very precise lattice structure. And so we talked a little bit in the beginning of class as diamond not being the thermodynamic form of carbon, and that graphite actually is. But then let's talk about carbon in terms of oxides. So carbon will react with oxygen to form acidic oxides, and carbon monoxide is extremely poisonous. The reason why is that it has really good binding affinity for hemoglobin, and so it will kick out oxygen because its affinity is better. So CO is also very reactive with oxygen, chlorine, metal oxides, and hydrogen in terms of being able to reduce those. So carbon monoxide will react with oxygen to form CO2. Carbon monoxide will react with chlorine to form phosgene or mustard gas. Carbon monoxide will react with metal oxides to reduce those down to the metal itself. Carbon oxygen will react with hydrogen to form methanol. So if you compare carbon monoxide to carbon dioxide is now dense and inert. So carbon monoxide has like a dipole, because carbon and oxygen are different in electronegativity. But in terms of carbon dioxide, your dipoles are going in opposite directions, and therefore the overall molecule has no dipole. And so you'll have unusual sublimation at normal pressures, so that's where you get that dry ice kind of subliming. And so this is kind of an interesting statistic. So 50% of carbon dioxide is used for refrigeration, and 25% is used for soft drinks. So that's actually quite a bit of carbon dioxide that goes to soft drinks. So carbon dioxide will react with limestone, water, and strong bases. And then it also, and that's in terms of like those things coming together. So the calcium hydroxide, limestone will form calcium carbonate, and then CO2 and water is going to make carbonic acid, etc. So then carbon reacts with halides, and these are great refrigerants. And so in terms of being able to keep things cold, you may not have heard about hydrocarbons. And these basically break up in the higher levels of the atmosphere to form that like chlorine atom that we've put in your ozone decomposition. Kinetics rates so much that you saw. So that chlorine atom, where does it come from? Is there just a bunch of chlorine up in the atmosphere? No, the answer is that you've got these chlorofluorocarbons, which are great refrigerants, which then break apart, atomize, and then tend to decompose ozone. So we're going to answer this question. Let's contrast the three main allotropes of carbon: diamond, graphite, and C60. So what is the difference? Well, diamond, you have networks that are in the lateral and the vertical direction. And so this allotrope of carbon is the most strong because all of your bonds are multidirectional. So that's that allotrope. The difference between diamond and graphite is that graphite only has bonding in the lateral direction. So you have sheets of lateral bonded carbon. So that's the difference between those two. C60 is this buckyball situation where everything is, the allotropes of carbon are such that they're sp2 hybridized in kind of a sphere that ends essentially in terms of how large the buckyball is. Okay, so let's talk about silicon. So in between silicon and germanium, silicon is just totally way more common than germanium. So it looks like a metal, but it has really low conductivity, and so it's a metalloid. And so in terms of the purity in computer semiconductors, it has to be extremely pure. And so the methods to purify it require it to go through to form the silica, but then that isn't pure enough, so they convert it to a silicon halide, and then they crash that back out as the actual silicon. So microprocessing requires a lot of purification steps to make sure that the silicon is at the correct purity level. Otherwise, your computer chips will be malfunctioning. So then silicon dioxide is SiO2. This is known as silica or quartz. Sand, as you know, it actually includes iron oxide impurities, but pure silica or pure quartz is just going to be SiO2. So then silicates are SiO4 4-, which is this tetrahedral type structure. And these form chains of polyhedra where you can have a bunch of tetrahedral structures that all come together. And so if you have a small change in structure, it leads to changes in toxicity. So blue asbestos is actually not toxic, and white asbestos is toxic. And the only difference between these two structures is your polyhedra chain kind of representations. So that's really the only difference is between those two. And people don't often know that, and so we just say asbestos, everything's bad, and we get rid of it all. Talcum powder is also kind of a silicate, and it has a slightly different structure. So the other thing that's true is that silica can be used to replace two of the oxygens on that tetrahedral kind of structure with carbon groups. And if you replace two of the groups with carbon, you end up with silicones. And silicones are going to be oils and rubbers, which are more resistant to oxidation. So this is your silicon metal right here in this picture. This is a quartz silica crystal, and then this is a silicone material right here. So silica is really very versatile in terms of what it can be used for and how it can be used. But if you compare silica to carbon dioxide or to carbon, you're not going to find silica as a gas. You're not going to find silica with multiple bonds to something. You're going to find single bonds of silica to something else, and this really changes the reactivity of carbon and silica as a result. Let's talk about tin and lead. So both oxidation states are possible, the 2 and the 4, for tin and lead, and both are stable. In most cases, these, even when they are with other nonmetals, these are mostly have covalent character to the oxides, and that's because these anions and the cations are very polarizable. And so even in high oxidation states, they're considered soft because their molecular orbitals are still pretty diffuse. So tin is a shiny metallic in its stable form, which is hard and malleable, and gray and crumbly in its brittle form. So this is a phase diagram for the tin. And so you see right here, this is the cubic form, diamond, and this is the tetragonal form, white tin. So this is the white, and this is the gray crumbly. So one of the interesting stories that have been talked about is whether or not part of the downfall of Napoleon's army in Russia was due to the temperatures and the changing in form of the buttons on the army's coats. So let's talk through this. Let's say that you go into a metalworking shop in the, I don't know about my history, 1600s, and 16, 17, and what you have is you've got shiny metallic hard malleable tin buttons, and you sew them onto everybody's coats, and that is stable at 18 degrees Celsius. 18 degrees Celsius is pretty good, like it's not too terrible. But when Napoleon's army was out in Russia, the temperature, got as low as like -5 degrees Celsius or -15 degrees Celsius. And so what happens is that you're going to have your tin changing from the white hard form to the gray crumbly form, which means that all the buttons were breaking, all their coats were opening, people had a hard time staying warm. This really causes a problem in terms of I don't know what the word is. It's like attitude or ability to fight if you're kind of like really cold and tired, that you're always having your buttons break. So that's the story there, and this is just a reminder on how to be able to read phase diagrams. So temperature here, pressure here. If I had a gray form at 200 K and I increased my pressure a ton, I could get it back to that tetragonal white tin. And this is also something that you hear when you hear tin screaming. It's because you're changing the phase between them. So temperature, if I go from 200 to 300, I'm going to have a change in the phase between my white tin and my crumbly gray tin. So tin 4 oxide is also used in glazes to make them stronger. So then lead oxide is the stable oxide, and then lead dioxide is a strong oxidizing agent. This is the one used in lead batteries. Many of you have already remember that from an exam where you looked at lead oxide and protons and sulfate, and that goes to lead sulfate and water, and then this is the other half of the equation. So, so this is used in lead batteries, which is really nice to be able to use that. So let's talk about CO2 and SiO2. So the oxides, carbon dioxide and silicon dioxide, adopt dissimilar bonding due to the following reasons. So carbon is a non-metal and silicon has more metallic-like properties. Carbon can form favored double bonds while silicon favors single bonds. Carbon has an expandable octet and silicon does not. None of the above, or A and B above. So I'm going to pause for a minute. Okay, so so A seems right. Carbon is a non-metal and silicon has more metallic-like properties. It's a metalloid, so that's gonna affect the bonding, right? So non-metals are gonna form are gonna be able to form double bonds. Carbon can form favored double bonds while silicon favors single bonds, so that's true. Carbon has a thermodynamic preference for forming double bonds in a lot of cases. Silicon prefers single bonds. And then carbon has an expandable octet and silicon does not, so that one is false. Carbon has a non-expandable octet because it's in that first row. Silicon does have an expandable octet. So one of the examples that we sometimes talk about is silicon hexafluoride, and that's going to be a super acid, but that's going to be an expandable octet where silicon has 6 bonds. So it's not D, it's going to be E, A, and B above. Okay, so let's talk about this other group. So we've got nitrogen, phosphorus. Again, these are going to be similar, but nitrogen is going to be different than phosphorus because the first element in every family is kind of weird. So then you've got arsenic and antimony, and then bismuth. So there's not really a clear division of properties between these groups. They kind of share and mix from a lot of places. And so again, the nitrogen and phosphorus are neighbors, but extremely different. And you're going to have high oxidation states for nitrogen, which are going to be unstable, but high phosphorus oxidation states are going to be stable. And so that's just a difference in kind of these two elements. Nitrogen has a very small charge density, and so again, it's going to be limited to 3 or 4 bonds. Phosphorus can have that expanded octet, and so 5 bonds to phosphorus is not uncommon. Nitrogen is much more electronegative, so if you're thinking about a nitrogen dichloride reacting with water to form ammonia and HClO4, this is not as reactive, but PCl3 plus 3H2O goes to H2PO4 plus 3HCl. This is an exothermic reaction. So in terms of electronegativity, the nitrogen kind of is more electronegative, so it's going to have lower reactivity when combined with halides. These can all be solids, so here's your phosphorus solid, your antimony solid, and your bismuth solid. And then here's a nickel, which is a gas, and then your arsenic which is a solid. So let's talk about nitrogen. Nitrogen takes a most common form with itself. So when you think about things bonding with themselves, we talked about catenation. So it only has one allotrope, and that's the N2. Nitrogen gas is colorless, odorless, inert. It does, in fact, undergo a few reactions, though. So lithium will react with nitrogen to form a lithium nitride. So that's where nitrogen has a -3 charge. Nitrogen can also react with oxygen to form NO2, which would be laughing gas. So these are reactions that are possible with nitrogen. And again, the Haber-Bosch process would be the major consumer of nitrogen to form ammonia. So that's also a process that we use nitrogen for. So the other thing that we should talk about for nitrogen oxides is that basically all of them are thermodynamically unstable but kinetically stabilized. So the decomposition of a lot of the oxides back into nitrogen is thermodynamically preferable, but just happens really slow. So here's some nitrogen oxides. So NOx, X is going to be 1 or 2, and these nitrogen oxides, NO or NO2, are both produced by vehicles, and they're pollutants. Nitric oxide is your air pollutant that basically happens here. So then it reacts with atmospheric oxygen to form NO2. So here's NO2. This generates ground level ozone, crop damage, greenhouse gas, and then N2O is nitrous oxide. That's your laughing gas. It's used in racing engines to increase power. It also can be an oxidant in the same way that oxygen is, but it just has kind of less oxidizing power. And then your nitrates and nitric acid is synthesized from ammonia and oxygen. And so the thing to remember about nitrates is that all salts that have nitrates in them are soluble. So let's see if we can answer this question. We've got NF3, which boils at -129 Celsius, whereas NH3 boils at -33 Celsius. Account for the difference. So if we think about those two numbers, the one that boils at a higher number is the one that has stronger intermolecular forces. And so NF3 versus NH3 is such that the NF3 has kind of weaker intermolecular forces, and NH3 has stronger intermolecular forces from the hydrogen bonding. So that's going to be the difference between those two. So let's talk about the rest of the group. Phosphorus, so we talked about nitrogen really taking only one form. Phosphorus can take two. The two main allotropes are the white phosphorus and red phosphorus. And so white phosphorus is this tetrahedral structure, and then red phosphorus is tetrahedral structures linked together in chains. And so these have really different properties. The white phosphorus is pretty stable, but then the red phosphorus is the one that's going to be used on the tips of matches. And so phosphorus oxyacids have unique structures. So when you're thinking about phosphate, you have PO4 3-. Phosphoric acid, all of the oxygens are protonated, and so you kind of have those hydroxides off of them. But if you think about something like phosphorus acid, then what you actually have is phosphorus directly attached to a hydrogen bond. And so that's kind of a unique structure that students often don't think about. So then phosphoric acid and phosphates can donate multiple protons or accept multiple protons. So we talked a lot about phosphates and the speciation according to pH and how that's dependent on that. And then we also have talked a little bit about phosphates in the body on exam, I think it was exam 1, maybe exam 2, where you have adenosine triphosphate, and we paired that up with a reaction that was non-spontaneous. So spontaneous and non-spontaneous processes can be coupled together. So phosphates in the body would be adenosine triphosphate goes to ADP. So ATP, ADP interconversion is how our body really uses energy, gets energy. And then arsenic is poisonous or medicinal depending on the concentrations. Bismuth can be used for stomach pain. So if you've ever wondered where that biz comes from, Pepto-Bismol comes from that bismuth in it, and it has antibacterial properties. So let's talk about combinations of hydrogen phosphate and dihydrogen phosphate ions are often used as buffers. Which of the following is true regarding these salts and buffer solutions? So a buffer made with a higher concentration of hydrogen phosphate compared to dihydrogen phosphate will have a pH equal to pKa1. A buffer made with equal concentrations of hydrogen phosphate and dihydrogen phosphate will have a pH equal to pKa2, or C, none of the above. So if you think back to making buffer solutions, your buffer solution, the pH of a buffer solution, let me get my cursor here, is the Henderson-Hasselbalch equation. So your pH is going to be equal to pKa log of A minus over HA, right? And so if this is the case, so a buffer made with higher concentration of hydrogen phosphate compared to dihydrogen phosphate will have a pH equal to pKa1. So hydrogen phosphate, 2 minus, and dihydrogen phosphate. And okay, so how do we decide if we need to use Ka1 or Ka2? So this, the HA and A minus combination of these two is associated with Ka1, and the combination of these two is associated with Ka2, right? So if I want to use hydrogen phosphate and dihydrogen phosphate, that is these, and so I need to look at Ka2. Therefore, this is wrong because that doesn't have to do with these two ions. And then the other thing is that your higher concentration makes it difficult to have those two things be equal, because if this is higher, then it's not going to be equal. But if they have equal concentrations, then that means that the log of 1 is equal to 0, and therefore the pH equals the pKa, and we just have to make sure that that pKa is equal to the right one, and it's pKa2, which is correct. Okay. Oops. Okay, so let's talk about group 16. So this is what's known as the chalcogen family. So we're going to focus on oxygen and sulfur. So oxygen and sulfur are nonmetals. Selenium has a lot of allotropes. Tellurium and polonium are similar, but polonium is really the only metal in the family. So, so sulfur versus oxygen. Oxygen is small. We have no expanded octet. It's a gas. The oxygen-oxygen double bond is stable compared to this triple and single bonds. So the single bond is what's known as kind of peroxides. That's going to be oxidizing. The triple bond is explosive. It's like so difficult to make, it's just going to explode. Sulfur catenates, so this means that you have chains of sulfur is most stable. So sulfur, actually the form that you see it most in is S8. Selenium is used in quantum dots and in glasses. It has a good band gap that allows photo processes, and then it's biocompatible, so you can actually get selenium in a lot of these cases, and it decreases cancers, or it says it does, at kind of low concentrations. And then tellurium is used as a color sensitizer, so not as useful. So oxygen, almost all of the elements react with oxygen except really the noble metals, and a small concentration of oxygen, in water supports life. So the solubility of oxygen in water is important. We talked about that in terms of like Henry's law. So ozone generated by oxygen is such that you just take oxygen and then the right amount of light with frequency, and that gives you your ozone. And then, and then it can form in, ozone can form in combustion engines, where if I have NO2, that this nitrogen oxide, right, so and nitrogen dioxide, then I form nitric oxide plus oxygen atom. That oxygen atom then reacts with oxygen to form ozone. So this is the chemical reactivity associated with that NO2 pollutant that can form ozone at low atmospheric concentrations. And so then your powerful oxidizing agent is ozone, which reacts with protons and electrons to form oxygen. And this has a standard potential of 2.07. So if you think about oxygen and its power, it's 1.23. So this is going to be a stronger oxidizing agent than the oxygen. So then destruction of ozone can happen with kind of a species halide. So if I have chlorine atom or fluorine atom in the atmosphere, that reacts with ozone to form XO and oxygen. And then that XO reacts with another oxygen atom to form more oxygen. So the ozone layer decomposition was actually pretty bad, but it's gotten a lot better. So here's 2019, it happens to look a lot better. We didn't get a lot of change through these years, but it got a lot better this last little bit. So let's answer this question. River and lake waters are commonly used by electrical generating plants for cooling purposes. Why is this a potential problem for wildlife? So we talked about that a little bit with nuclear chemistry. When you're doing a nuclear reactor, usually the cooling water is coming from a lake or a stream. And so electrical generating plants are going to often just pull water from wherever they are and then pull them back on. That's why electrical plants are often near bodies of water, because you can just use the water that's there. But in terms of wildlife, this could be a potential problem if you're not actually watching the amount of water that's coming in and the heat transfer and mass transfer of that cooling water. So, why do we care? Why would that matter? So if you think about it in terms of the water temperature, then what matters and why it's important is that as the water temperature increases, you have less oxygen that can be dissolved in the water, and therefore this is going to mess up your oxygen availability for wildlife within that water, essentially, which then, bothers animals that are feeding off of the fish or whatever in the water, et cetera, et cetera. Okay. So we're going to watch this movie on separations of amphoteric hydroxides, but before we start, so antimony hydroxide and tin hydroxide are insoluble in acidic conditions. And so if you start with something that's acidified and you have solids already in it, those are likely going to be antimony hydroxide and tin hydroxide. So you can convert the tin hydroxide, make it soluble by taking it to a basic solution, because the hydroxide basically reacts with the tin in the same way that we talked about hydroxide reacting with boron, to make a negatively charged cation that goes into solution. But antimony won't do that type of reactivity. So basically in basic solutions, tin is going to act as Lewis acid, hydroxide is going to act as Lewis base, where you get this now soluble anionic complex tin hydroxide anion. But this doesn't happen with antimony. Aluminum hydroxide will precipitate at a neutral pH, while zinc will form a complex with ammonia and go into solution. So we're gonna see this real quick. Let me whoa! Sorry about that.
This is actually acidic. So in this case right here, we have a precipitate. These are actually antimony and hydroxide.
Okay, so here's my my tin and my antimony that are both in there already, and they're acidic.
Quickly spin those out.
And so those are being separated as the solids in acidic solution. They're being removed from there, and then you're gonna basically take the two and be able to separate them by making it basic. So I think we're gonna do that in a minute. Yeah, so here's my antimony, here's my tin, they're both in there. I'm gonna take pH 10, which makes them basic. That's gonna convert my tin to that hydroxide, which is now gonna go into solution, and I can now separate my antimony and my tin, which is good. I guess if you make it basic enough, you can also convert your antimony over. Okay, so we separate those out. Lots of switching happening. So then the antimony sulfur is a nice orange solid, while the tin sulfur is a yellow solid. And so that kind of also lets you look at the difference between those two. So here's alumina and zinc. If you take your pH to neutral, then your aluminum will stay in solution, and then you can complex that zinc. Oh, sorry. So then you can get it out. Okay. So let me stop sharing that. Close that. Whoa. Okay, so that's how you can think about separations for amphoteric hydroxides. So let's talk about sulfur. Sulfur catiinates again to form S8. Molten sulfur is used in vulcanization, which just means the hardening of rubber and in dyes. And so here's your antimony sulfur complex. Here's your tin sulfur complex. So one is orange, one is yellow. Here's your mercury sulfur complex, which is black. And so hydrogen sulfide is kind of this rotten egg smell. It's produced naturally by anaerobic bacteria. Sulfides are mostly insoluble, so the sodium sulfide is soluble and is used as a high-performance battery, which is really nice. But sulfur usually is kind of used for quantitative analysis to get things out. Sulfur oxides are going to come from coal combustion. They have acid rain consequences because they're going to be forming sulfur trioxide, which then reacts with water to form sulfurous and sulfuric acid. So sulfates are mostly water soluble and they're not oxidizing or reducing, and therefore they don't alter the pH and they're thermally stable. So because of these properties, why would you think that sulfate ion is commonly used in chemistry? Let's say I need to increase my concentration of some sort of cation. I can use sulfate as my counter ion because I know that it's going to be water soluble, it's not going to be oxidizing or reducing, it's not going to change my pH, it's going to be thermally stable. And so for all of these reasons, that sulfate ion is commonly used in chemistry. And that is all of our questions. So all of the presentation for main group metals. So some questions to think about is why is aluminum a particular environmental problem in the context of acid rain? If you have CO with metals, it's the carbon atom that acts as the Lewis base. Many of you are going to want to say that the oxygen is what binds as the Lewis base. But if you write out a formal charge representation, you can answer this question a little bit better. So draw out that Lewis acid, draw out that Lewis structure, and think about what side has the actual formal negative charge. So contrasting properties of CO2 and SiO2, explain why you have such dissimilar bondings. That's similar to the practice problem. Thinking about what is the Lewis acid and what is the Lewis base in the reaction of chloride and tin chloride to form tin trichloride anion. So give reasons about which one is the Lewis acid and which one is the Lewis base. When NO and air are mixed, you get N2O4 and NO2. However, NO produced an auto-exhausted part per million concentration only reacts very slowly with the oxygen in the atmosphere. Suggest a possible mechanism for the reaction and explain why the reaction at low NO concentrations is so slow. So that's kind of a kinetics problem for you to think about in terms of why that would be slow. Okay. So, so with that, I'm going to stop recording, and hopefully that gives you a little bit more insight into the main group metals, how they react, kind of what you can expect in terms of questions, and we'll be happy to answer any more questions about main group metals. But hopefully you get an idea of kind of how we're relating the periodic table elements and their reactivity back to things that we've already talked about in class, in terms of kinetics and phase diagrams and separations and solubility. So these are all things to kind of think about in terms of what the final exam is going to look like. So hopefully you guys have a good afternoon or morning or evening, and I will talk to some of you later and some of you not ever again. So have a great rest of the semester.